Hello friends, so today we are going to solve the questions from the year 2012, total 6 questions. From 2013, we are going to have 3 as mains question, and 3 will be from advanced. So for 2013 we are having 3 from the mains and 3 for the advanced. So total there are 12 questions. So the first question, it was asked in the year 2012, and it states that consider a thin spherical shell of radius r with its center at origin carrying uniform positive surface charge density. The variation of the magnitude of electric field given as E of r and electric potential given as V of r with the distance r from the center is best represented by which graph? So indirectly it is asking for how the electric field and potential is going to vary in case of this thin spherical shell with respect to radius, and the graph for the magnitude of electric field and potential are plotted on the same graphical scale, you can see. So from the left axis is representing our electric field, and the right axis is being represented as our electric potential. So this is directly based on the formula itself. So we know that the electric field inside the shell is 0. So we know that electric field inside the shell is 0, or from here we can say that our E of r will be equal to 0 under the condition that our small r is less than equal to capital R. So therefore we can just find out for electric field, and from here we can clearly see that option B cannot be correct option, neither the option C can be the correct one. Only option that provides us that the electric field is equal to 0. So this is the graph for electric field. This is 0 for when r is our less than capital R, less than equal to capital R, and same C we see in the our option number D also. Okay. So this is our part. So B and C cannot be the options. So only option correct will be one of from A, or it can be D. Now we come to the outside of the, you can say, the shell. Therefore electric field outside the shell that is our E of r will be equal to k q upon r square, and this is for when r, small r, is greater than equal to capital R, or basically we are only interested in the with respect to radius. So we can just write it that our E of r is proportional to 1 upon r square. So there is inverse relationship between the electric field as well as the distance and the square of the distance. Okay. So both A and D represent the same graph for electric field. Okay, it suddenly increases to a maximum value and then is a rapid decrease with respect to the square of the distance. So now we have to find out the potential. And for potential, you can say electric potential inside the shell is constant. And is equal to and equal to potential at the surface. Potential at the surface. So from here we can write our V of R will be equal to our K Q upon R, and under the condition that our R small r is less than equal to R. Okay. And here we have to remember that this potential is constant, okay, and is equal to the potential at the surface. So this formula represents the potential at the surface, and it will be same that is our inside the shell also. Therefore, the only option that is a correct one is option number D, because here the potential is constant up till the surface, that is where R is equal to small r, and after that it decreases. Okay, slope is on the, you can say, lesser side as compared to our electric field, because here it falls by 1 upon R, that is our outside part also. We can write it if required. So we can say electric potential at outside we can write this as our V of R is equal to K Q upon small r, and this is for R is greater than or equal to capital R. Therefore, we can write that our potential V of R is proportional to 1 upon R. Therefore, option D is the correct one. Option D is correct. Next question. It was asked in the year 2012, and it states that in the given circuit, a charge of plus 80 microfarad is given to the upper plate of a 4 microfarad capacitor. Then in steady state, the charge on the upper plate of 3 microfarad capacitor is. Basic circuit is given to us. So we have a 4 microfarad capacitor. Let us call this as our C1. Charge on the upper plate is given as plus 80. We have 2 capacitors. 3 microfarad, let us call this as C2, and 2 microfarad, let us call this as C3. So we have to find out in steady state the charge on the upper plate of our 3 microfarad. Here C2 and C3 are parallel with each other. And we have to remember that in case of capacitors, one part is very important, that is our conservation of charge. So total charge in a closed system, if there is no addition or subtraction, then the total charge on the entire system is always conserved. Okay. So we have to remember this thing. Most of the question for the capacitor, we are able to solve it by using that the charge in the system is going to be conserved. If there is no, or we can say if it is isolated system or a closed system, once it is capacitor charge is given, supply is removed, then the charge will be remain constant no matter how many capacitors we connect to that particular charged capacitor. So we have to remember that total charge in the closed system remains constant. Total charge in a closed system remains constant. And in this case, as soon as we connect C1 to the C2 and C3, so this 80 microcoulomb charge will be distributed across the entire system, but total sum will be still equal to 80 microcoulomb because the initial charge on C3 and C2 is not mentioned, but we are presuming that it will be equal to 0. So first of all, let's find out the equivalent capacitance of the parallel combination. So you can say our C equivalent will be equal to C2 plus C3, and that is our 2 plus 3 microfarad, giving us 5 microfarad. It means the total charge on the parallel combination, because of the conservation, the charge on the parallel combination is also 80 microcoulomb. Okay. Now we can easily find out the so here now we are going to get the circuit we can redraw. So this is our C1, and then we have our C equivalent. So here we are having plus 80 microcoulomb, and this is our C equivalent. So the total charge will be our, so let me write it. So we can say total charge is conserved, therefore you can say total charge on the parallel combination, total charge on parallel combination will be equal to plus 80 microcoulomb. Now we can easily find out the voltage across the parallel combination. Voltage across a parallel combination, and we can say, let us suppose that is given as V. So V will be equal to our, let us call this as Q total, QT. So this will be our QT divided by C equivalent, and this comes as 80 microfarad divided by 5 microfarad, giving us 16 volts. So we have the parallel combination, that is C3 and C2. So the voltage across C3 will be our 16 volt, and similarly voltage across C2 will be also our 16 volt because they are in parallel. So now we can just easily find out the charge on the capacitor C3. charge on capacitor V 3 microfarad, that is C3, will be equal to, let us suppose we call this as Q3, will be equal to C3 multiplied by V. And we already know that our C3 is 3 microfarad and voltage over 16, so this comes as 48 microcoulombs. So option number C is the correct option. C is correct. Next question. It was asked in the year 2012 and it states that two large vertical and parallel metal plates having separation of 1 centimeter are connected to a DC voltage source of potential difference X. A proton is released at rest midway between two plates. It is found to move at a 45-degree to the vertical just after release. Then X is nearly equal to. So here we can just draw the approximate figure, and we are given two plates, and these two plates are connected to a external voltage source, potential difference rather, and that is given as X. So this is X. So therefore our left side will be positive and our right side will be our negative. So electric field will be from our left to right. So we are going to get our electric field in this direction. So obviously the force due to electric field will be also in this direction, that is our Fe, that will be equal to Q times E. And it states that proton released midway, it moves at an angle of 45-degree with the vertical. So suppose this is the position of the proton and it is moving in such a way that making the angle of 45 degree with the vertical. So let us draw a vertical here. So it will be moving at angle of 45 with the vertical. So this is a vertical 45, and this is the, you can say, resultant velocity in which the proton is moving. And there will be two forces acting on this proton. One force will be because of electric field, that is our Fe, and the other force will be because of the weight, that is our mg. Okay. And we can also say that this angle will be obviously equal to 45. So the resultant of both the forces will be, let us suppose that is given as of Fr, and this will be the resulting force which makes the proton to move at angle of 45-degree with the vertical. And suppose d is the distance between the plates, then we can write that our electric field will be equal to the potential difference, that is X upon d. And from here we can find out the force due to electric field acting on proton will be equal to our Qp multiplied by our electric field. So we can write this as our Qp multiplied by X divided by d. And the force acting in downward direction will be equal to, let us suppose we call this Fg. So we are having that gravitational force that is of Fg will be equal to mass of proton multiplied by g. Mass of proton multiplied by g. Okay, and this is charge on proton. And the angle between the two is given as 45. So, sorry, the angle is between the two is coming as 90 degree. Okay, because resultant force is towards 45 with the vertical, so the angle between the two will be coming as 90 degree. Therefore, we can say that our since proton moves at 45 degree, therefore we can write that the force of the electric field should be equal to force because of the gravitational force. This is Fg. We simply substitute the values. We get this as charge on proton multiplied by electric field. Sorry, electric field we always sorted out. X upon d is equal to mass of proton multiplied by g. And we are interested in finding out of x. So we can say that our x will be equal to, this comes as our mass of proton multiplied by g multiplied by d divided by charge on proton. And now we simply substitute the values. Mass of proton is our 1.67 into 10 to the power minus 27 kg. G is our 9.8 and D is given as 1 centimeter, so this comes at 10 to the power minus 2 meters. And charge on proton is our 1.6 into 10 to the power minus 19 Coulomb. So this gives us that our X is approximately equal to 1 into 10 to the power minus 9 volts. So option number C is the correct one. Option C is correct. Next question. It was also asked in the year 2012 and it states that 6-point charges are kept at a vertices of a regular hexagon of side L and the center O as shown in the figure. Given that K is equal to 1 upon 4 pi epsilon naught multiplied by Q divided by L square, which of the following statements is or are correct? So here it is mainly talking about the electric field and the potential. Potential at origin, that is O, and along PR and along ST. So it says that it has 6 and they are kept in a regular hexagon. Okay. And if we look closely, we can clearly see that this hexagon is mainly consisting of the dipoles. Okay. So we have plus Q, minus Q, plus 2Q, minus 2Q, and plus Q and minus Q. And first case, we are going to find out electric field at O along OD. Okay, so we need to find out the electric field at point O, net electric field, along with its direction. And we are mainly interested in towards OD, and later on we can say multiply it. So therefore, we can just draw an approximate figure. So we have a center O and there is a charge of minus q here, and this is our also minus q, and we are having a charge of minus 2q here. Okay, so this is our E, this is our D, and this is our C, and the angle between our E and C, this angle will be our 120 degree, and we can just easily find it now. And we can just okay, so this is our O, and the electric field in this direction, let us call this as electric field because of E, and in this direction let us call this is our electric field because of C. And here we have to remember that the electric field because of plus q, which is here, let me draw that charge also. So this point is our F, and charge is our plus q, and the electric field because of this plus q will be also along our EC in this direction. Let us call this as EF. Okay, so electric field because of this will be along same lines, that is our EF, and then we are having the other end, that is also a plus q, and its electric field will be also along EE, and let us call this as EB, and finally is our point A, and this electric field will be also our EA, and this electric field is our ED. So from here we can write that our electric field, let us start with our D. So we can say electric field due to charge at D will be equal to, that is equal to 2 times K, and EA will be also in the same direction, so we can write our EA will be also equal to 2K. So we can write further electric field because of charge at E will be equal to our K, and electric field due to our charge B will be also equal to K. And finally we are left with EEB, and we are left with EC and EF. So we get this, our electric field C will be our K, and electric field due to our F will be also our K. So therefore we can summarize this electric field in terms of like this. So along D we are going to have electric field that will be equal to summation of this 2K as well as 2K, okay, and will be giving us 4K. And next here also we are going to have electric field will be over 2K towards our E, and electric field of C, this will be also our 2K, and the angle between them two is equal to 180 degree, 120 degree. Now we can find out the resultant of the electric field because of this OE and OC, and we can just divide into two components. This will be one and this will be the second one, and net will be, because the you can say this vertical, let us call this electric field due to our OE, and this is our Y component, and this will be electric field our OC, and this is our Y component. And here we are going to get our electric field our OE X component, and from the other side we are going to get our electric field because of our OC and its X component. And the resultant of, you can say that our EOE X component will be our, this is 2K and 2K, and we are going to get this as our K, and similarly we are going to get our electric field because of our OC in X direction will be also equal to K. So net electric field, so this value is also K and this value is also K, therefore we can write, and we have to remember that the angle between the two is 120 degree, and these two will balance out each other, Y component. So we get our net electric field in the direction of OD will be equal to, we already have 4K plus K and plus K, so this gives us 6K. Therefore is along OD, option A is correct. Option A is correct. Next, it says that potential at O, it means center, is equal to 0. And for part B, we can say that potential at 0, and that is center V0, will be equal to our K times, we have this is charge at A divided by L plus charge B divided by L plus charge at C divided by L plus charge at D divided by L, and this is our charge E divided by L plus charge, and this is our F divided by L. And we can easily substitute the values. We get this as V0 will be equal to K upon L. Charge on A is our plus 2Q, and A is our plus 2Q, B is our plus Q, C is minus Q, and D is our minus 2Q, and E is our minus Q, and F is plus Q, minus Q and plus Q. So here this plus 2 and plus minus 2 goes away, and this also cancels out. Therefore we get that our V0 will be equal to 0. It means potential at our center will be equal to 0. So option B is also correct. Option B is correct. And next it states that potential at all points of PR or second in D in ST is same. So PR and ST, okay. And for this is our part C, and here we have to remember that all these charges are arranged in the form of a dipole. So on the one side we have this plus Q, minus Q, and here it is a minus 2Q, and this is our plus 2Q, this is our plus Q, and here is our minus Q. So all these are nothing but our dipoles. And if this is the center, and through here we are having a line that is our PR. Okay. And we know that this PR line is equatorial line for all the dipoles. So if we consider a dipole of Q, this upward, that is our plus Q and minus Q, this line is the equatorial line. Similarly, this entire line is equatorial for all the dipoles. So you can say the PR is equatorial line of the dipoles. And we know that for the equatorial, you can say, line, the potential, this is acting basically equipotential surface. So the potential on this entire line will be same. You can say same potential. Therefore, option C is also correct. Option C is correct. But for ST, the line ST is given something like this. So this is our ST, and we already know that the electric field, the resultant electric field of this entire system is towards in this direction, which was previously we called this as OD, and the direction of OD is same as the direction of our ST. So the electric field, net electric field, will be from S to T, and we know that the potential decreases along the electric field line. So therefore option D is our incorrect. So we can write that electric field will be directed from S to T, and potential decreases along the electric field line. Decreases along the electric field line. Therefore option D is incorrect. Option D is incorrect. Next question. It was asked in the year 2012, and it states that a cubical region of side A has its center at the origin. It encloses three fixed point charges minus q at 0 minus a by 4 0 plus 3q at 0 0 0 and minus q at 0 plus a by 4 and 0. Choose the correct option. So here we are given, no doubt a cubicle is given to us, but all the charges are lying along our y-axis only, at the origin inclusive. So therefore, in order to find out, and these options are all related with our net electric flux. And for net electric flux, we can easily use our Gauss law. And Gauss law states that the net electric flux will be dependent upon the total charge enclosed. Okay, so let's find out the total charge enclosed, or in this case we can say net charge enclosed. We can say net charge enclosed, and that is our q enclosed will be equal to minus q plus 3q and minus q. This gives us q. Therefore, we can say that the total electric flux using Gauss law we can write that our flux total will be equal to our q enclosed and divided by epsilon naught. Q enclosed is our q plus q rather, and divided by epsilon naught. Now we are going to find out what will be the net flux with respect to all the respective axes. Okay, and we have to remember that the center of this entire cubical region is at the origin. Okay, so center is somewhere here, and so we can say this box is symmetric about all the axes. So we can say that this is given a cubical region is symmetric. Okay. So the first we are given that along x-axis, and along x-axis we have a plane that is our x is equal to plus and x is equal to minus a by 2. So we can write for plane along x is equal to plus minus a by 2, and with respect to the plane of plus minus a by 2, we can clearly see that all the charges are our, you can say, in y-axis. Okay. So we can say since all the charges are aligned along y-axis and symmetrically placed with respect to x is equal to 0, and symmetrically placed with respect to x is equal to 0. Therefore, we can say that the flux with respect to x plus a by 2 will be equal to flux with respect to x minus a by 2. So therefore, the option number A is correct. Next we come to the, we can say, the plane y is equal to a plus 2 and y is equal to a minus 2. Next is our plane along y is equal to plus minus here it states that net flux crossing plane y is equal to a plus 2 is more than the net flux crossing the plane at minus a by 2. In the first case it was equal and it is saying it is more. So plane along y is equal to a plus 2, and here also because of the symmetry the flux because of symmetry we can write that a flux y equal to plus a by 2 will be equal to flux y minus a by 2. It is not greater than, neither it is less than. Therefore option B is incorrect. And we come to the option C. Before that, let us analyze, you can say, option D. Because it is based on symmetry and our is, you can say, plane is along, and that is given as z a plus 2 and x is equal to a plus 2. X is also a plus 2 and z is also equal to a plus 2. And in this case also the configuration is symmetric about both x and z direction. So we can say that configuration, that is cubical configuration, is symmetric about both x and z direction. Therefore flux along x is equal to plus a by 2, a is equal to flux along z is equal to plus a by 2. Therefore option number D is also correct. And C is obviously correct because we just proved it by using the Gauss law. So C is also correct. So option A, C and D are correct. Option A, C and D are correct. Next question. It was asked in the year 2012 and it states that an infinitely long solid cylinder of radius capital R has a uniform charge density of rho. It has a spherical cavity of radius r by 2 with its center on the axis of the cylinder as shown in the figure. The magnitude of electric field at a point P, which is at a distance of 2r from the axis of the cylinder, is given by the expression 23 rho r divided by 16 k epsilon naught. The value of k is. So basic figure is given to us, infinitely long cylinder, and it is of radius r, cavity is there of radius r by 2, and at point P the electric field is given to us by the expression. So basically we are going to find out the net electric field at point P, and because of the cylinder as well as the cavity. So we are going to equate to the given expression. From there we are going to find out our k rather. So here this is, you can say, directly based on the formula, and we know that electric field due to infinite cylinder, and we also know the electric field due to a sphere. Okay. And basically this is cavity, so the difference will be of the, you can say, the electric field due to cavity will be the negative of that of the equivalent to that negative charge is enclosed inside this cavity. So let us start with formula. We know that electric field because of the cylinder at a distance r is given as rho r square divided by 2 epsilon naught small r, and this electric field because of the sphere, it is given as k q upon r square. This is the general formula, and the important part is that the electric field due to a cavity is the negative of the field due to charge that would fill the cavity. Negative of the field due to charge that would fill the cavity. So indirectly means if there would have been no cavity, so if we assume that the charge density on this cylinder is positive, so automatically the charge density on this you can say circle, or here it is cavity, will be coming as minus of rho. Okay, that's the basic meaning of that. And let us reformulate both the formulas according to the question, and here that our small r will be equal to 2r. So we can just write it that electric field due to the cylinder will be coming as rho r square divided by 2 epsilon naught, and this comes as 2r, which comes as rho r upon 4 epsilon naught, because quite simple, this r goes with a square. And next we can find out the electric field due to the cavity, and the radius of cavity is our r by 2. So let me write it here. Here this r is equal to 2r. Okay, and we come to the next part, that is electric field due to the spherical cavity at point P. Electric field due to cavity at point P, and the distance from the center is given as 2r of point P. So we are given that distance of point P, it is given to us as 2r. Okay, and we have to find out the you can say charge on the cavity, and that charge will be dependent upon the volume charge density, that is our rho, and multiply the volume of the cavity. Okay. So distance is given as 2r, and next we are going to find out the volume of the cavity. Volume of cavity, let us call this as V cavity, which will be equal to 4 by 3, and the radius is given as r by 2 whole cube. So this comes as, this is 4 and cube 8, 8 and 4 and 2, so this comes as our pi r cube divided by 6. Now we can easily find out the charge on the cavity. Charge of the cavity, let us call this as Q cavity, which will be equal to charge density, volume charge density, multiplied by volume of the cavity. So we get this as Q cavity will be equal to rho multiplied by pi r cube divided by 6. Now we can find out the electric field at a distance r, small r rather. Okay, so we have to keep track of the small r and capital R. Therefore we can write that the electric field because of the cavity will be equal to 1 upon 4 pi epsilon naught. Charge is our Q cavity, and our r, small r, is equal to 2r whole square. This comes as 1 upon 4 pi epsilon naught. Q cavity is our rho pi r cube divided by, this comes as 4r square, and multiply by 6. And we can just cancel this r square, take us away our cube, and pi goes with pi. So we are left with this as rho r, and this comes as 96 and times epsilon naught. Now we are going to find out the net electric field. Net electric field at point P, and let us call that as our EP, which will be equal to electric field because of the cylinder minus electric field because of the cavity. We just substitute the, we get this as EP will be equal to, this is rho r upon 4 epsilon naught minus rho r upon 96 epsilon naught. So this gives us as 23 rho r times 96 epsilon naught, and we can just compare it with our given, and we are given this as 23 rho r 16k epsilon naught. Rest of things are same, only difference is the denominator. So this is 23 rho r 16k epsilon naught. So we can say our 16k is equal to 96. So from here we can say our 16k is equal to 96, gives us k will be equal to 96 upon 16. Sorry, this is 16, giving us k is equal to 6. So value of k is our 6. Next question. It was asked in the 2013 mains, and it states that two capacitors C1 and C2 charged to 120 and 200 volt respectively. It is found that by connecting them together, the potential on each one can be made 0. Then we have to find out the relationship between this C1 and C2. So we can just draw an approximate figure. So this is our C1, and it is charged to 120 volt, and then we have our C2, it is charged to 200 volt, and therefore we can from here find out our, we can say the charge on them. So we can say our Q1 will be equal to C1, let us call this as voltage as V1, and this voltage as our V2. So Q1 will be equal to, and this is our Q2. Q1 will be equal to C1 into V1, which gives us 120 times C1. Similarly, our Q2 will be equal to C2 times V2, which gives us 200 times C2. And it is given when they are connected, the potential on each can be made equal to 0. Okay. And which basically means that for the charge to be conserved, okay, because they are not connected with anything, before and after the charge should be, their sum should be equal to 0. Therefore, we can write that final potential is our 0. Therefore, we can say total charge should be also equal to 0. Therefore, we can write conservation of charge that is our initial total charge will be our Q1 plus Q2, final total charge is 0. So from here we get that our Q1 will be equal to minus of Q2. We substitute the values, we get this as 120 C1 is equal to minus of 200 C2. Now it is quite easy to solve. This 0 and 0 goes away, and this goes by 3 and this goes by 5. Therefore, we can write this 3C1 is equal to minus of 5C2. So if you want to write our magnitudes only, this can be written as 3C1 is equal to 5 times C2. So we have 3C1 5 times C2, and option number B is correct. Option B is correct. Okay. And anything else? One second. There is okay. So if charge is like plus minus and we want that their potential should be equal to 0, then it should be connected like this. And if we use this is, let us suppose V1 and this is our V2, so from here we can say that our this is our minus of V1 and this is also minus of V2 is equal to 0. So we can say V1 plus V2 is equal to 0. And this gives us that V1 is equal to minus of V2. Okay. So minus V2 yeah, this looks good now. This is because from the looks of their potential will be equal but in opposite sign. And so because from here if this condition holds, then this C condition is also going to hold. Okay, and this makes the situation very tricky. Okay, because A and D are certainly not of the options, but if this condition hold, then we are going to have this is 3C1 plus 5C2 will be equal to 0. So option C will certainly going to hold. Okay, but this is not the correct option, so I have to make some correction in it, and that correction arises that the charge will be equal to minus of minus. Yes, so we can put here a minus. This comes as minus of minus, that will be plus, this will be plus, this will be plus, and this will hold. So because V1 is equal to minus of V2, the charge polarity will be reversed. So we have to take care of that, because then this option is incorrect and this is also incorrect. So option B is the only correct option. Okay, that was a mistake on my part. Next question. It was asked on the year 2013, and it states that two charges each equal plus q are kept at x is equal to minus a and x equal to a on the x-axis. A particle of mass m and charge q naught, which is equal to minus q by 2, is placed at origin. If the charge q naught is given a small displacement y, which is very much less than a along the x-axis, the net force acting on the particle is proportional to. Okay. Sometimes this type of question is also asked, you can say, with respect to the SHM also. Okay, SHM or periodic or both. And we can just draw an approximate figure for that. So initially we are given that we have two charges. So this is our minus a, this is your plus a, charge is our plus q here also and here also plus q, and q naught is kept at the origin, and this is our y-axis, this is our x-axis. And the second part, this q naught is moved slightly upward by a distance of y. Therefore we can just redraw the same. So this is our plus q at the position of minus a, this is also plus q at a distance of plus a, and now our charge q naught, let us suppose, is somewhere here, and this distance is our y. So we can just join them, and we have to remember this y is our minus of q by 2, negative charge. Okay, and this distance will be our a, and here this distance will be also our a. Therefore let us call this as our r. Then our r will be equal to a square plus y square and its square root. And let us assume it is making an angle of theta with the y-axis. So therefore both the charges are opposite, so they are going to attract each other. So let us suppose it is having a force F here, and other side also there will be equal force, that is F. So independently we can just draw it, and this is our charge q naught, and we are having a force F here and F on the other side, and angle with the vertical we have assumed is our theta. So we can divide this F into respective coordinates. So one force will be in this direction, that will be F sine of theta, and in this direction we are going to have F cos of theta, and because of the other end we are also going to get F sine of theta, and here also we are going to F cos of theta. And this F sine of theta and F sine theta are obviously going to balance each other. So this is our q naught, which is our minus q by 2, and this is our plus q, and this is our also plus q. Distance is given as a, and this distance is also our a. And we have a small angle. A small angle we can just sort it out later on. Now we can easily find out the force F. We can say that force F will be equal to k q multiplied by q by 2 divided by r square, that is a square plus y square. And this we can write it as that the force F will be equal to K, and this comes as our Q square. This is 2x square plus y square. And from small angle we can say that our one second. Cos of theta, we can say our sine of theta is equal to so the net force F net will be equal to 2F cos of theta, and F we just found out, so we can write this as 2 multiplied by F is our K Q square upon 2 times x square plus y square, and we can substitute our cos of theta, and cos of theta, one second, okay, theta is here, so this comes as y upon yes, this was the mistake, this is our a, not x, so this comes as a square, now it's correct, so this comes as a square plus y square and 1 by 2. So therefore this 2 and 2 cancels out, so we get our F net is equal to K Q square upon a square plus y square and whole raised power 3 by 2 multiplied by y, and we are given that this y is very much less than a, therefore from here we can write that our a square plus y square whole raised power 3 by 2 can be approximately equal to our square, this goes away, and a cube. So we get our F net will be equal to K Q square upon a cube multiplied by y, which gives us that net force is proportional to our y. So option number A is the correct one. Option A is correct. So one second, let me check. Sorry, my mistake. Here the force is along minus y-axis. I forgot to add that part because it is acting in lower direction, so we are going to get this as F net will be equal to minus and this will be over minus and this is minus, so we get option B is correct. This is the correct one. Next question. It was asked on the year in the year 2013 main, and it states that a charge Q uniformly distributed over a long rod AB of length L as shown in figure. The electric potential at a point O lying at a distance L from the end A is. Basic figure is given to us. We have a rod of length L and we have to find out the electric potential at the distance L. Okay. So if we measure the distance with respect to this point, so we are going to get this as 2L. Okay. And so this end will be our 2L and this end we already know is our L, because this is going to help us in the integration part. So let us assume that we have taken a small portion of this rod whose length is our dx. This is our A and B, and this is our point O, and this dx is at a distance of x. So because of this small element and this dx is having a charge that is our dq, therefore we can find out that our potential, that is our dV at point O. So we can say, consider a small element dx, charge dq at a distance x from O. Therefore, small potential dV will be equal to k multiplied by dq divided by distance x, and dq is with respect total potential, total charge is q, so we can say our dq will be equal to our total charge q divided by length and multiply by dx. So we can say the total potential, that was electric potential due to rod of length L at O. Let us call that V naught. And this V naught will be equal to integration from L to 2L, and we have this as k dq upon x, and k will be our constant. So let us substitute it. This comes as k, or let us keep it inside still, and we can write this as our L to 2L. This is our k, and we have q, dq is our q into dx divided by L multiplied by x. And now let us sort it out. So we get our V naught will be equal to, this is k is 1 upon 4 pi epsilon naught, and this is q upon L, and integration of L, and this is 2L. dx upon x. So integration is nothing but our natural log of x. So we get this as 1 upon 4 pi epsilon naught q upon L. This comes as natural log of x. Limit is from L to L. And now we can just substitute the limits rather. This comes as 1 upon 4 pi epsilon naught q upon L, and this comes as natural log of upper limit is 2L and divided by our L. This L and L goes away. So we get this as V naught will be equal to 1 upon 4 pi epsilon naught q upon L and natural log of 2. So this comes as q upon 4 natural log. Option number D is the correct option. Option D is correct. Next question. It was asked in the year 2013 advance, and it states that two non-conducting solid spheres of radius r and 2r having uniform volume charge density ρ1 and ρ2 respectively touch each other. The net electric field at a distance 2r from the center of the smaller sphere along the line joining the center of the sphere is 0. Then the ratio of ρ1 and ρ2 can be. Okay, so we have to find out the ratio of ρ1 and ρ2, and we can just draw the figure. So we have a smaller and we have a bigger one. They are touching each other. Radius of smaller one is given as r, and the radius of larger one is given as 2r. We have to find out net electric field at a distance 2r from the center of the smaller sphere. So this is center of smaller sphere. So we have to find out the net electric field at a distance. Let us suppose we call this as point P, and this distance is about 2r. But in this case we are not mentioned to which direction this point P is. And similarly, there will be another point somewhere here. Let us call this as point as Q, whose distance will be equal to also 2r. This is r, so this will be also over r. So it means there are 2 points P and Q, and here this electric field is equal to 0. And from the smaller sphere we assume that the charge is Q1, larger charge is Q2, and the sigma 1 is a charge density here, sigma 2 is our charge density. Therefore we can easily find out that our ρ1 will be equal to Q1, and this is over 4 by 3 pi r cube. So we get that a Q1 will be equal to 4 by 3 pi r cube multiplied by ρ1. Similarly, we can find out our ρ2. ρ2 will be equal to our Q2, and this is our 4 by 3 pi r, and here radius is given as 2r whole cube. So this gives us our Q2 will be equal to, this comes as 832. So it comes as 32 by 3 pi r cube multiplied by ρ2. So we found out the charges on the smaller and the larger sphere. And the electric field, general formula we already know, that electric field is equal to Q, K charge divided by radius square. So because of the smaller one, we can say electric field at point P due to smaller sphere, let us call that as E1, which will be equal to k q1, and distance is our 2r and its whole square, which will be coming as k q1 upon 4r square. Okay. And the direction will be towards the right. Okay, direction we can write later on also. Now we come to the larger sphere. Big sphere, and electric field, let us suppose given as E2, will be k times q2 divided by distance, and so distance comes as from 1 second, there is some so from the center. Okay, yes, so we need the distance from the center here. So this distance, so we already have this as 2r up till here, and this is our 3r, 4 and 5r. Okay, so this distance is our 5r. So we get this as 5r whole square, giving us k q2 upon 25r square. And it says that net electric field should be equal to 0. Therefore, we can say that our net electric field, let us suppose given as E net at, let us call this EP. EP is equal to 0. So we can say our E1 minus E2 will be equal to 0. And simply substitute the values. So E1 we got is our k q1 4r square. So this comes as k q1 4r square minus k q2 25r square is equal to 0. And from here we can write that our 25 into q1 is equal to 4 times q2. q1, q2 we already know. So we substitute, we get this as 25, and q1 is our 4 by 3 pi r cube, rho 1 is equal to 4 32 by 3 and pi r cube, and this is our rho 2. Pi r cube 3 3 4 4 pi r cube cancels out. Therefore we get that our ratio rho 1 upon rho 2 will be equal to 32 upon 25. Okay. And here we have to take care that in order to for its net electric field is to be 0, so the electric field should be acting in the opposite direction. Okay. It means if one is acting towards the our left side, then other one will be acting towards the right side. Okay. So it means it has to be oppositely charged. Therefore, the actual ratio will be coming as minus of 32 divided by 25. So one of the option B is the correct one. Now we come to the point which is our internal, that is our point R. So here we can say our 4-point R, even that is a smaller sphere, the distance is same, it's not going to change. So this comes as q1 upon 4r square. And for the larger sphere, obviously the distance is going to now change. So this comes as our k q2 divided by, one second, yes, so this point R is lying inside this sphere, okay, larger one, and radius of this sphere is our small r, sorry, capital R. Therefore E2 will be in ratio. Okay, so this will be K times our Q2, and this will be our multiply by R, and here will be coming as 2R whole cube. This will be coming as K Q2 divided by 8R square. For the largest sphere, we have to remember that the point is inside the bigger sphere. Okay. So in proportionality, the charge is going to change, and obviously the electric field is going to change. And the net electric field, that is of ER, will be equal to, once again, E1 minus E2. This will be coming as KQ1 divided by 4R square minus KQ2 divided by 8R square, and it is said to be equal to 0. So this gives us that our 8Q1 is equal to 4 times Q2, which gives us that 2Q1 is equal to Q2. Now we can easily substitute value of Q1 and Q2. So this gives us that twice Q1 is our 4 by 3 pi r cube multiplied by rho 1 is equal to 32 by 3, and we have this is pi r cube rho 2. 4 by 3 pi r, and this 3, sorry, this goes by 8 pi and r cube. This cancels out, and we get, and further this is about 2 and this is 8 goes by 4. So therefore we can say that our ratio rho 1 upon rho 2 is equal to 4. So option number D is correct. Option D is correct. Next question. it was asked in the 2013 advance, and it states that in the circuit shown in the figure, there are two parallel plate capacitors, each of capacitance C. The switch S1 is pressed first to fully charge the capacitor C1 and then released. Switch S2 is then pressed to charge capacitor C2. After some time, S2 is released and then S3 is pressed. So after some time, we are going to find out what will be the charge on respectively C1 and C2, specifically the upper plates. So basic figure is given to us. Switches are 3, S1, S2, S3. Two voltage sources, twice V0 and V0 is given. Capacitors are C1 and C2, each is having capacitance of C. But here the key point to remember is that our V0, the polarity of the battery position is opposite. Okay, because this is going to help us to solve in the final step when S3 is closed. So in the first part, it says that S1 is pressed and released. S1 is pressed and released. Therefore, we can say that the capacitor C1 is fully charged. C1 is fully charged, and that will be charged to twice V0. In the second case, we are given now S2 is pressed. S2 is pressed. For this, we can just draw the figure also. So this is our S1. It is pressed and released. So with the fraction of second, the capacitor C1 is going to charge to a voltage of twice V0 in the fraction of second, because there is no resistance, something like that. When S2 is pressed, the circuit will be now like this. So we have our C1 and it will be positive. So this is our twice V0, and here we are having our C2. And as soon as S2 is pressed, the charge will be equally distributed between C1 and C2, because so you can say S2 is pressed and fully charged. Yeah, I missed one thing. I missed here C, and this will be our twice CV0 because it is charged. And when S2 is pressed, the charge on C1 will be equally distributed between C1 and C2. Charge on C1 will be equally distributed between C1 and C2. Therefore, we can say that charge on C1 will be equal to CV0, and charge on C2 will be also equal to CV0. So we get the charge will be CV0, and here also CV0. And now S2 is released and S3 is plus. S2 is released and S3 is pressed. Therefore, we have our C2, this end will be positive, and through switch S3 a battery of reverse potential is connected, that is our V0. So here this is our S3. Now in this case, as soon as S3 is pressed, first, because the polarity of this capacitor volt, you can say it is given as CV0, is opposite to the applied voltage, that is V0. So first it is going to discharge and then it is going to charge in the reverse direction. So we can say that C2 discharges through V0 and charges again to, we need to find out the charge, to minus CV0, minus CV0. Okay, so therefore the new charge on the upper plate will be of minus CV0. Okay. This is our C2. So option number, the charge on the upper plate of C2 is our minus CV0. So option D is correct, and charge on upper plate of C1 is our one second. C1 was having a charge of, C1 charge is equal, okay, so this is our CV0. So we have option B is correct. So option B and D are correct. Option B and D are correct. Next question. It was asked in the year 2013 advance, and it states that two non-conducting spheres of radii R1 and R2 carrying a uniform volume charge density plus rho and minus rho respectively are placed such that they partially overlap, as shown in figure. At all points on the overlapping region, we have to find out the electrostatic field as well as electrostatic potential. So basic figure is given to us. So this is a common, and here we are going to find out the electric field as electrostatic field as well as electrostatic potential. So we know the basic formula, that for non-conducting uniformly sphere, you can say electric field inside a non-conducting uniformly charged non-conducting uniformly charged sphere, the formula is our E depending upon the radius R will be equal to our rho divided by 3 epsilon naught and we have this is R vector. Okay. And the direction will be dependent upon this rho, because we are mainly interested in magnitude and direction. Magnitude we can say, and we can say direction will be dependent upon the value of rho. If rho is positive, that is greater than 0, then direction will be radially outward. And if this rho is less than 0, then it will be inward. And remember, we are considering here the point is inside, because this the you can say overlap area, the point is inside the sphere. Okay, so at a distance of r. So for the overlapping region, let us consider that the position of the point is at a vector position r1 for sphere 1. Let us call this as sphere 1 and this sphere as 2. So we can write that r1 is the position vector of a point from the center of sphere 1. Similarly, we can say our r2 is the position vector from the center of S2. And we can say that electric field at any point in overlap, let us call that as E net, will be equal to E1 plus E2. We substitute value of E1 and E2. We can write this as our rho 3 epsilon naught, and we have this R1 vector plus minus of rho 3 epsilon naught, and we have this as R2 vector. Therefore, we can write our E net will be equal to, and we can take this is rho upon 3 epsilon naught as common. This comes as R1 vector minus R2 vector. And let us assume this R1 minus R2 is represented by D. Therefore, we can say that our E net will be equal to R2 minus R1. So E net will be coming as minus rho upon 3 epsilon naught and our D unit vector. And we are interested in our magnitude. So here we have written that for any point inside the overlapping area. Okay, so for any point, the difference of R2 minus R1 will be always equal to D. Okay. So it means this our E net will be uniform for, or we can say same for all points in the overlapping region. Okay. So if you want to write its magnitude, we can write our E net will be equal to rho 3 epsilon naught and magnitude of our D. Therefore, for direction, we can say from the center of positive to the negative sphere. From center of positive to negative sphere. And nature, we can say uniform, which basically means same at all points in the overlapping region. Same at all points in the overlapping region. And so we found out that our electric field is constant in magnitude, okay, and the direction will be same, that is from the positive to the negative. So C and D are the correct one. And next we are find another thing, that is our electrostatic potential. Okay, electrostatic field is not zero, obviously A is incorrect. So from here we can say option B and D are correct. C and D are correct. And now we are going to find out the potential. Relationship we already know. We know that our electrostatic potential, we can say our E is equal to minus delta of our V. And we have our electric field is uniform, therefore we can write our potential will be equal to minus of E r vector and some plus constant. Okay. So we can say that in the overlapping region, the potential decreases uniformly. Along the direction of electric field. Along the direction of electric field. Therefore, only it's electrostatic potential is constant, so this is also incorrect. So only option correct are our option C and D are the correct options. So these were the questions. Total questions were 12. From the year 2012 we are having 6 questions, and from 2013 mains we are having 3 questions, and from 2013 advanced we are having 3 questions. So total our questions were 12. So this complete all the 12 questions. Thank you.